Okay, how do ILOps work? Well, we've already talked about how to do that in a single processor, right? We detect an illegal operating system, and we're going to force a procedure call. They're discovered in the RF stage, right? That's when we actually, for the first time, have the instruction and are busy decoding it. So that's it's in the RF stage that we're going to detect that we actually have an illegal instruction. And now the question is, what should we do about it? Okay, we have an instruction in one of the pipeline stages that seems to be, we can't execute it. So what's our strategy for dealing with instructions we can't execute in the pipeline stage? Well, if we can't execute them because we just have to wait for a while, we employ a stall strategy. But if we can't, we'll never be able to execute this illegal operation. In fact, we need to do something else entirely. What should we do? And the answer is, we're going to, oops, I skipped past the magic answer. The answer is we're going to synthesize an instruction to replace it. And the goal of this new instruction should be, its only purpose in life is to capture the PC plus 4 value. Right? So we're going to take the illegal operation, which is now in the RF stage, and replace it with this instruction here, which you can see it doesn't branch. R31 is never not equal to 0. And so we're not going anywhere. This branch is really but the other side effect of the branch, besides changing the PC value, is to write PC plus 4 into a register. So we synthesize this instruction, and the rest of the pipeline stage will go, oh, for me, what this means is to capture the PC plus 4 value in the XP register. So that's the purpose of this rewrite. So in fact, the multiplexer here that's busy rewriting the instruction in the register file stage. So we had one input here that rewrote it as a no-op. We also have a way of rewriting it as this magic B&E with the destination register of the XP. That's what this here is. And then when that makes its way down the pipeline, that'll capture the PC plus 4 value, which is exactly in the XP register, which is exactly what we did in our standard implementation, right? We just have to sort of shuffle our feet a little differently here because we have to let that happen not in this stage when we discovered the error, but we have to send a message way down here to make sure the WD cell mux is set correctly and the register file writes the XP register. And the way we sent that message down 2 pipeline stages was simply to synthesize an instruction that says, when you get this, do this, and you'll do what I want. Does everybody sort of get that idea? The whole goal here is to send a message a couple pipeline stages down, and the way we're doing it is rewriting the instructions so the pipeline stages will do what we had in mind as the result of the illegal operation. Okay, well, it turns out that ILOps aren't the only reason you might not be able to complete the execution of an instruction. In the ALU stage, what might happen? You might divide by 0. You might have some sort of error that says, look, I don't have any good number to write into the destination. I want to stop execution of the program at this point and instead go off to some sort of kernel trap handler that can print you a backtrace or make Python print a backtrace or something that noticed that instead of failing silently and writing garbage, the arithmetic unit may say, this is not legal. I'm going to stop your program execution so you can go figure out what's wrong. What sort of operation might go wrong in the memory stage? We can think of 2. One is you might access an illegal memory address. The bottom 2 bits aren't 0 of your address, or you're accessing a region of memory that's not there. Or, it might not, you have a memory management, you might have to be taking a page fault. So once we have the address, we go check the page map. It's not resident, so we want to take a page fault. So we really can't execute this instruction here, whatever it was, the load or the store. So in fact, what we need to do is to stop execution. We need to rewrite the instruction where the fault was discovered into one of these magic B&Es, please capture PC plus 4 for me, into the XP register. And what do we do with all the instructions that are behind us in the pipeline, that became after us in the program? What should we do with them? So we're down here, we're saying, oh gosh, this load, we can't finish that, we have to take a page fault. What should we do with the instructions that follow the load? They're in the pipeline. Well, should we execute them? How many people think executing is a good plan? That sounds like a very, medieval sort of statement. Kill them all! That's not what I meant by executing. Should we actually do the instructions? No. So the thing is that we're stopping the program execution at this load instruction. All of these instructions that follow the load are like they shouldn't be executed. So we mean execution in the other sense, right? We need execution in the. We need to stop executing the instruction. We don't want to execute any of those instructions. How do we arrange for an instruction to go away in the pipeline? Replace it with a no-op. Okay, so, you wander around and everybody's sort of saying, oh gosh, that's a bad idea. You can say, replace it with a no-op. And everybody will go, whoa, boy, of course 6 people are strange. Okay. Okay, but now you have a new term. I'm going to no-op an instruction, which basically means I'm going to take it out of the pipeline and replace it with a harmless thing to do instead. So this operation of when you detect a fault, rewriting that to capture PC plus 4, so that means execution is now halted here, and flushing the pipeline. So we're going to take all the other instructions that come earlier in the pipeline. Okay, that means they come after the faulting instruction in the program. They're earlier in the pipeline. With all of those instructions. What about the instruction down here in the write back stage? That's okay, it can finish. It was okay instruction, it's just finishing up. So whenever the fault happened, we rewrite it with a BNE, destination register of XP, and we throw away everything else. We flush the pipeline. So these sorts of traps are expensive. I mean, we're throwing away lots and lots of execution. Typically, they represent an error condition or a condition that will take hundreds of instructions to fix, like a page fault. So throwing away 3 and 4 instructions is not a big deal in the scheme of things. Yes, ma'am?
When you come back, will you then have to skip backwards because...
Right, so the PC plus 4 is actually pointing to the instruction after the one that stopped. So in these particular faults, we have to basically say, ooh, guess what? We actually have to back up the XP and to see where the actual faulting instruction was.